All right. Let's go ahead and talk about 4.1 Introduction to Apportionment. So now we're moving along the semester, and now we're going ahead and talking about some applications. So, first thing we're going to talk about is voting and apportionment. 4.1 is going to focus on, well, as you can see here, apportionment, whereas the next section is going to focus on voting. So, first off, what is apportionment? Well, to give us a definition of apportionment, this is the mathematical investigation in which we take a whole and divide it into various parts. Or in more common terms, for example, let's say we're talking about the US Constitution, and apportionment is essentially, in layman terms, how many representatives should each group, or in the US, how many representatives should each state get if we're deciding it, for example, based on population. So in 1790, the House of Representatives, first attempted to apportion itself. And there were a lot of different ways that people proposed on how to apportion and decide how many representatives should each state get. So actually, through all of this debate, two plans kind of came out as forerunners. One was put forward by Alexander Hamilton, and the second was put forward by Thomas Jefferson. So we're mainly going to focus on that of Alexander Hamilton, but we are still going to reference Thomas Jefferson's method. So to really get into this, let's go ahead and talk about a little bit of a scenario. For example, what if I have this fictional country, Andromeda, and suppose it's got 5 states and the total population is exactly 20,000. And among those 5 states, they have a population distribution as shown below. For example, Apis has a population of a little bit over 11,000. Libra has a pretty small population of 879. Then Draco, Cephus, and Orion. So each of these states have various populations. And then we're going to try to see if my constitution for my fictional country of Andromeda says I need 25 representatives for these 5 states. And suppose that I want to apportion them, that is, I want to distribute my representatives according to the state's respective populations. So some preliminary information here. If we're going based off population, from these 5 states, I definitely see that Libra is the smallest state, whereas Apis is the largest state. So I'm kind of expecting Libra to have the least amount of representatives, and Apis to have the most. But our question really is, how many exactly should we be giving them? So, going forward with the Hamilton plan. If we discuss the Hamilton plan, we have a couple of steps for us to discuss. The first step of the Hamilton plan says, take the total population and divide it by the number of representatives. And we actually call this the standard divisor. So if we're talking about our country, we have 20,000 people, and we wanted 25 representatives. Therefore, we're going to take 20,000 divided by 25. And I'm going to show that on screen in just a moment. What does a standard divisor mean, and why do I even mention this? Well, ideally, this standard divisor gives me the number of people that each representative should be, well, representing. So in my fictional country, let's take 20,000 divided by 25. If I do that, 20,000 divided by 25, I get actually exactly 800. This tells me, since the standard divisor is 800, for each of these 25 representatives, each one should be representing roughly 800 people. Of course, we can't get this number to be exactly perfect, where 800 people exactly, but we should be in this ballpark where each person is roughly, each representative represents 800 people. So that's going to be our step 1, getting the standard divisor. What's step 2? After we get the standard divisor, we need to get what we call the standard quota. This is, we take the standard divisor, and then we divide the population of each state by that standard divisor and round down. We call this the standard quota. So Let's see what does this look like for our fictional country. If I look at my fictional country, I took the population, as you can see here in this second column, and then I take the population divided by the standard divisor. So for example, for Apis, I took 11,123 and divided it by 800. I did the same thing for Libra, Draco, Cephas, and Orion. I divided each population by 800. And I get some decimal value. In this first row, Apis, we get 13.904. The standard quota is us simply rounding down. I'm going to say that again. We are rounding down. We're not rounding up. So 13.904, if we round down, we get 13. For Libra, 1.099, we round down. Same thing for Draco, Cephas, and Orion. So the standard quota tells me this is sort of our starting point for how many representatives we should be getting. So if I look at this, Apis so far has 13 representatives. But let's see what happens. If I add up all of these standard quotas, 13 plus 1 plus 4 plus 1 plus 3, then I'm going to get a total of 22. But how many representatives did we really want? We wanted 25. So we've got a little bit of a problem. We wanted 25, but I've only got 22 accounted for. What happened to those remaining 3? Well, to counter this, the Hamilton plan did have a little bit of a contingency plan. What the Hamilton plan said was, we look at the decimal portion, and from the greatest decimal portion to the least, we assign one extra representative. So in this case, we need 3 more representatives. So I'm going to look at the 3 states with the largest decimal portion. So the decimal portion means everything after the decimal. So for example, Apis, we got 0.904. Libra, we got 0.099. Then 0.398, 954, and 646. We're going to go down the list and see which one has the greatest decimal portion. Well, from these 5 states, the greatest decimal appears to be 0.954. That's my first largest one. And the Hamilton plan says, well, let's give it 1 extra representative. So instead of 1, we're going to give them 2 representatives. And then we're going to continue forth until we've assigned the remaining 3. So I needed 3 more. I finished 1. Now I need to assign 2 more. From these remaining 4 states, we're done with Cephas. Which one has the next largest decimal? Well, the next one I see is Apis with 0.904. Therefore, I'm going to add 1 to the standard quota. So instead of 13, I have 14. That finishes up for Apis. And now I need to look for the third largest decimal. I have 0.099, 0.398, 0.646. Well, I think we can pretty much agree that Orion has the largest decimal. Therefore, I'm going to go ahead and add +1 to its number of representatives. So again, I was missing 3, and this is how I assign those missing 3. If I was missing a 4th one, I would go to the next largest decimal, which would be Draco, for example. So looking at this, I have my final number of representatives, and they add up to 25. This is our Hamilton plan. So let's summarize. In this Hamilton plan, the steps that we followed were, first off, get the standard divisor, which was again, total population divided by my apportion amount. That is how many representatives I wanted. Step 2, give me the standard quota by dividing the state population by the standard divisor and then rounding down. And then if I have any remaining seats that are left, I distribute them one by one to the states with the largest decimal remainder. So this is our Hamilton plan. Now let's go ahead and talk about our alternate version, the Jefferson plan. So, one of the weaknesses of that Hamilton plan was we often end up with a couple of remaining seats, and then we had to distribute one by one. So, Jefferson proposed a different version, which is actually very similar. In the Hamilton plan, again, we had some unfilled seats. So, Jefferson proposed a modified standard divisor. So, this modified standard divisor said instead of doing these calculations to get the standard divisor, we're going to do some trial and error. In other words, we almost have the exact same process, but we guess, in a sense, the standard divisor. And one thing about this Jefferson method is that we could possibly be using more than one modified standard divisor that will work. So if I go back to my fictional country Andromeda, I could do some trial and error, play around with a lot of divisors, and let's say I end up with 740. In this table, if I divide by 740, then as it turns out, my number of representatives do add up to 25. So I do have a couple of issues with this Jefferson plan, though. The biggest one is that it boils down to pretty much a guess and check. There's no process for saying, how do I know 740 right away? Other things is that 741, 742, I believe, as well would work. So we don't have an exact value. But this does avoid the question of what if there are leftover representative seats? And just to show the difference between these two and their final results, in our fictional country, again, Hamilton plan, we had 14,1,4,2,4 for the number of representatives and how they're distributed. Whereas the Jefferson plan, Apis actually had 15 representatives instead of 14, and Orion had 3 instead of 4. So there is some differences between these two. They can come up with much different results. So for our class, we're really going to focus on the Hamilton plan, but it's good to mention the Jefferson plan as well. And you're going to see what I mean by that in this example. So let's say I'm working with Reuben County and their environmental agency. And there are 5 major cities in this county. Let's say that they want 18 members on the board for the environmental agency. And they want to make sure that the cities are represented appropriately. The cities are Cardiff, Salona, Vista, Palma, and Pacific. And those are their respective populations, as we can see here in the table. So in this example, let's say we use the Hamilton method to determine the number of board members each city should have. We're not going to really use this Jefferson method, but you could go ahead and complete part B as well through some guessing and checking. We're mainly going to focus on this part A. So how do I proceed with the Hamilton method? I'm going to go ahead and pull up this table just so that we have it. Remember the steps for the Hamilton method. Step 1, what is my standard divisor? So my standard divisor, I don't have much room here on screen, but I'm going to write it up top here, so you'll have to bear with me. The standard divisor was the total population over the number of representatives. So what's my total population here of the entire county? Well, if I want the total population, I know the population of my 5 cities that we're accounting for. I'm going to go ahead and add these up. And I'm going to add these up off screen. So we have 7,020 plus 2430, 1540 plus 3720 plus 5290. If I add these up, I get a total population of 20,000. That's my total population. And how many representatives did I want? Remember on that previous slide, I wanted 18 representatives. So I'm doing 20,000 divided by 18. So what does that get me? Well, that's going to get me about 1,111.111 repeating. So I'm going to use 4 decimals. So remember, this standard divisor tells me that each representative should be representing roughly 1,111 people. So what do I do with the standard divisor? We move into the quotient. So I'm going to start filling out this table. I'm going to go ahead and take each city population and divide by my standard divisor. And I'm going to round to 4 decimals. You probably could do 3 and it would suffice, but 4 should be more than enough. So 7,020 divided by my standard divisor, we get about, let's see, about 6.3180. Again, I'm just using 4 decimals. If you are doing these calculations for me, there are more decimals, but 4 should be sufficient. I'd probably even argue that 3 would be more than enough in most cases. So I'm going to do the same thing for each of these. For the sake of notes, I'm going to go ahead and write these out. A little bit tedious, but that's okay. So each value divided by standard divisor. 111, 111, 5290, 111, 111. So go ahead and calculate these, and I'm going to go ahead and slowly write them on the screen. For Solona, we get 2.1870. For Vista, we get a value of about 1.3860. For Palma, 3720 divided by this 1000 value, we get 3.3480. Draw that a little bit nicer. And then 5,290 divided by my last value, we get 4.761. So I have my quotient. And now we find our standard quota. Remember, to get the standard quota, we round down. So for Cardiff, we got 6.318. We round down to give me 6. And I'm going to do the same thing for each of these. So let's count how many representatives do we have. We have 6 plus 2 plus 1 plus 3 plus 4. I've got 16 seats taken. I have an issue. We needed 18 representatives, but I've only got 16 accounted for. Therefore, we have to look into our last step. From these 5 cities, we look at the top 2 cities with the largest decimal portion. So if I look at all 5 of these quotients and their decimals, it looks like Pacific has the largest decimal, followed by, it's a pretty close race, but it looks like Vista is next. So those are the top 2 decimals. So I'm going to add 1 to their portion. Therefore, instead of Vista getting 1, they're going to get 2. And Pacific, instead of 4, they're going to get 5. And then the leftovers, well, they get the same amount. Let's just double check real quick and see, do we truly get 18 board members? 6 plus 2 plus 2, we get 10. 10 plus 3, we get 13. 13 plus 5, we get 18. So we have our number of representatives, or number of board members in this case, using the Hamilton method. All right, so as an exercise, if you want, you can go ahead and try to do the Jefferson method. Again, the major difference in the Jefferson method is that instead of finding a standard divisor, you do some trial and error and try to see if you can find an appropriate one, such that whenever you take the standard quota, it does in fact add up to a nice 18. So I'm not going to do this on this lecture, but you can take some time, see what it does for you. Next, I want to go ahead and talk about two little notes. The first thing I want to talk about is this thing called the Alabama paradox. The Alabama paradox states that if I increase the total number of available representatives or seats, as it turns out, sometimes it causes a state to lose some of its seats overall. What do I mean by that? In other words, I don't remember off the top of my head how many representatives the state of Alabama gets, but actually in 1880, they found out that if overall they increased the total number of representatives for the entire country, Alabama actually ended up losing some representatives somehow. But that doesn't make much sense initially, right? You should be thinking, well, more representatives overall means that each person should get the same or more representatives. So in 1880, Seton found that Alabama would lose a seat if the number of seats were 300. I can't remember off the top of my head what was it before, but it turns out that Alabama does lose, which is a little bit contradictory, which is why we call it the Alabama paradox. The second thing I want to mention is this quick thing I'm going to call the quota rule. So whenever I'm doing these seats and deciding how many seats or representatives each state should get, we should have a little bit of some checks and balances and make sure that we're being roughly fair in how we distribute seats. So to help us a little bit, there are some flaws. An apportionment plan should satisfy what we call the quota rule, which says the number of representatives apportioned to each group, or in our case state, is either equal to my standard quota or at most one more than the standard quota. And we saw this earlier. Yes, I did add a seat, but it was only at most one more than what we initially calculated. So this is our quota rule. All right, so this is our very, very brief introduction to apportionment and how we distribute seats to ensure representation. Besides that, I'll see you in the next video.